Okay guys, so today we're going to be learning all about trigonometry, and in the next few videos that's what they're going to centre on. Now trigonometry is difficult, you're going to use it a lot in A2 if you're going on to that, but especially with regards to C2 it's probably the most difficult topic. So it's really important that we get the foundations right in order to understand what's really going on. So to start with, I'm going to show you the kind of thing that you want to work up towards. So eventually you will be able to solve something like, that's a theta, something like that, given this range. Okay, so the question's asking what values of theta make this true given this range. Now at the moment this looks ridiculously overbearing, no idea where to start, okay, but don't worry, that is our eventual goal, to lead up to something like that. And it's going to get even more complicated than that, okay, but if we start building it one step at a time, it's alright. So let's start off with the graphs that you must know from GCSE. So if anyone asks you to draw the sine, cosine or tan graphs, you tell them, I can't do that, because they haven't given you a range or a domain. So I'm going to specify that this can only be drawn between 0 and 360 degrees. So that would look something like this for the sine graph. Now remember what this y-axis represents. This represents the proportion, doesn't it? That sine x equals the opposite over the hypotenuse. So this proportion can only go between 1 and -1. And let's see why that is. Well, it's actually quite obvious if you look at it, because the hypotenuse by definition is the longest side of a triangle, isn't it? A right angled triangle. So if I drew one, normally we would take from SOHCAHTOA our angle x here, and this would be our opposite, and this would be our hypotenuse, wouldn't it? So obviously sine x will give us opposite over hypotenuse, and this has to be less than 1, doesn't it, because the hypotenuse is the longest length, so it's always going to be something divided by something bigger, so it must be less than 1. The only case that it wouldn't be like that is if we had our angle in question being the right angle, so let's call this angle theta. So in this case sine theta would be opposite, well the opposite angle, the opposite side, sorry, is the hypotenuse, isn't it? And the hypotenuse of course is the hypotenuse, so this must equal 1. So you see the sine graph can never ever go beyond 1 or lower than -1. So if you ever have sine x equals 3 over 2, it's not valid, okay? It can't be that. So let's continue with our sine graph. Let's notice a few things. So it has a maximum here at 90 degrees and at 1, and it has a minimum here at 270 degrees at -1. It crosses the x-axis at 0 degrees, 180 degrees and 360 degrees. Do you see? Okay. So that is the sine graph. And of course this graph goes on forever, doesn't it? It goes on forever. If I didn't specify a range, it goes on forever. Like so, doesn't it? Yeah? Now an important thing to notice from our special triangles is that we know that, say, right, I'll draw my special triangle. So this is 60 degrees, 30 degrees. We know this is 2, √3 and 1, okay? So I know that sine 30 degrees equals opposite over hypotenuse 1 over 2. So if I drew 1 over 2 here on my graph, and then drew dotted lines, you see it hits here, doesn't it? At 30 degrees. But also, look, it hits here, doesn't it? And if I go along, it hits here it hits here. So you see, it's constantly, there's more than one solution, isn't there? It depends on the range. So if I extended my range from 360 to say 720, which is here, I can see that there are 1, 2, 3, 4 different solutions, can't I? So it's not just sine 30 degrees equals a half, it's also this angle here would be 150 degrees, so sine 150 degrees equals a half. And this angle here, this would be 390 degrees, sine 390 degrees equals a half. And also this one here, this one here, which must be 360 plus 180 is 540, so it must be 510 degrees equals a half. Do you see? So this range is really, really important. Okay, so you can only see that there are just, if I cut this off, there are only 2 solutions between this range. Okay, so this is called a mini trig equation. If they ask you to find the value of sine x equals a half between the range 0 and 360, you can immediately say, okay, so x must be 30 degrees and x must be 150 degrees. That is solving a mini equation, okay, a mini trig equation. Okay, so before we move on to the cosine graph, let's just make a couple of observations about the sine graph. The sine graph has what's called period 360 degrees. Now this is absolutely so important that you remember that. Period 360 degrees, that means it repeats itself every 360 degrees. Okay? Yeah, I think that's all we need to mention for the sine graph actually. Let's look at the cosine graph. So the cosine graph, very similar to sine, goes between 1 and -1. We speed up this time. Need a range. 360 again, between 0 and 360. And this time it crosses at 90 degrees to 70 degrees. So that's 360 it ends, and 180 is its minimum, and at 0 it has its maximum. Okay? So, there we go, that's the cosine graph. Can you see any kind of similarity between this and the sine graph? I hope you can. The similarity is that for starters, the cosine graph also has period 360 degrees. Additionally, you can see that actually the cosine graph is just the sine graph but moved to the left. You see, this has been moved to the left to get the cosine graph, doesn't it? So I can actually say that cos x equals sine, and we're going to use our transformations, aren't we? So if the graph's moved to the left, sine x plus 90 degrees, yeah? So the cosine graph is sine x plus 90 degrees. It's obviously been a translation by vector minus 90 degrees, 0, you see, of sine. So that's that observation. Absolutely need to know the graphs. And similarly, if I had a half here, you can see in this range there are 1, 2 solutions, exactly the same as sine. There are 2 solutions in this range between 0 and 360. And finally, let's look at the tan graph then. So the tan graph looks a little something like this. Okay, so it has an asymptote at 90 degrees, and it has an asymptote at 270 degrees. We know what asymptotes are now. Okay, and finally, touches there. Because again, I'm stating my range as going between 0 and 360 degrees, but of course it goes on forever. So the difference this time is that the y-axis goes on from infinity to minus infinity. So it doesn't go between 1 and minus 1 like it does for cosine and sine graphs, and you can work that out logically why that is. I'll let you think about that. So this time, what's really important about tan is that it has period 180 degrees this time, so half the period of the sine and cosine graph. Really, really important that we remember that. Okay, so the foundation of everything we need to know are the graphs and the trig identities. So now we're going to learn the trig identities. The first one you need to know is that tan x is always equal to, that's what those three lines mean, always equal to sine x over cos x. Okay? And we can prove that, can't we? We can prove that because we know that sine x equals opposite over hypotenuse, and we know cos x equals adjacent over hypotenuse, and we know tan x equals opposite over adjacent. So if I put sine x over cos x, yeah, I get O over h divided by A over h, which that would flip over and go over, wouldn't it? So I would end up with O over A, which of course is tan x. So we've just proved our first identity, that tan x is always equal to sine x over cos x. Really, really important that we remember this because you're going to be doing things like proofs in the next couple of videos. So number two, the second identity, is that sine squared x plus cos squared x is always equal to 1. And we can prove that as well. So again, sine x equals O over h, cos x equals O over, A over h, sorry. So if we whack them together and square them, we get O over h all squared plus A over h all squared. So that's sine squared plus cos squared x. So just to bear in mind that sine squared x, it's just the notation used, but this is sine x all squared, okay? Don't be put off by this squared there and it won't work in the calculator. You need to put sine x, whatever the angle is, all squared. So if it was sine squared 30 degrees, this would be sine 30 degrees all squared, okay? Anyway, so back to this. So if I square them all together and add them together, I get O squared over A squared over H squared. And of course, from Pythagoras, I know that O squared plus A squared equals H squared, doesn't it? So that's H squared over H squared, which is 1. So this proves both our identities. So these two absolutely must know. Okay? What we can do with this tan one is we can now show why the graph of tan has asymptotes at 90 and 270 degrees, can't we? Yeah? Because if we look at this, right, tan x is always equal to sine x over cos x. Well, at tan 90 degrees, so if we're looking at this point here, this is sine 90 degrees over cos 90 degrees. Well, I know from the cos graph, which looks like that, doesn't it? At 90 degrees, cos 90 equals 0, so this would equal, and sine 90 equals 1, doesn't it? So this would equal 1 divided by 0. We can't divide by 0, so it's undefined, and that's why we have this asymptote here. And similarly, we'll have the same asymptote at 270 degrees.